Hey, Pivot students, it's Steve, ready for another scintillating conversation about statistics. And I'm looking at myself on the camera here, and man, it looks like I could really use a haircut. But that's not going to happen for a while. All right, so the goal today is to, or at least in this video, is to work on the normal distribution some more. We're in topic 12, and we're one of the things we're doing is we're extending the big idea of the empirical rule. So you remember the empirical rule that says that if you have a normal distribution, then we can say something about the number of observations that are within, one standard deviation or two standard deviations or three standard deviations of the mean. In that sense, all normal distributions are universal. You can talk about proportions and percentages within those ranges. And what we're going to do here in topic 12 is extend that so that we're no longer stuck with working within one or two or three standard deviations. That we can look at fractions of standard deviations and calculate percentages that way. And in that sense, this will be a really useful tool for us. Okay, so we're going to get into it. We're going to work on some version of activity 12-1. So let's flip over there. Okay, so activity 12-1 involves a couple of scenarios, but I want to focus on the body temperature scenario. Okay, and I've posted a PDF of the problem and all the questions on the problem that I want you to address. And so it's helpful to have that when you're working through the activity. Okay, so here's a scenario. All right, we've got the body temperatures of 130 healthy adults. Okay, and that's the histogram of those body temperatures. Okay, and the mean is 98.249 degrees, and the standard deviation is 0.733 degrees, and that's of the people in the sample, right? Okay, we're going to answer a whole bunch of questions about that scenario. All right, but one thing to notice right away is the approximate shape of that distribution, right? So keep that in the back of your head. All right, so first question, kind of a softball warm-up question. So what are the observational units in the histogram, and what's the variable? Okay, so you know the observational units are the healthy adults, 130 healthy adults, right? And our variable is the body temperature, right? Because as we go from healthy adult to healthy adult, the thing that's changing is the body temperature. Okay. All right. Now I'm going to flip over to my hard copy of the problem so that we can work through it and we can write on it. Okay. So the goal of the problem is to calculate some proportions of people in different ranges. Okay, and we're going to do that two different ways. Okay, let me see if I can zoom this in just a little bit, and we'll back it out when I put up my larger slides. Okay, but again, if you have a hard copy available or online, it's useful to have that accessible. Okay, so first question. Actually, 2, 3, and 4 on this on the activity are review, right, about reading histograms. So it says determine the proportion of the 130 adults that had a temperature below 97.5 degrees. Okay, so remember it's a frequency histogram, so it's giving us the number of adults in each of these approximate ranges, and we're fortunate 97.5 comes on a nice break point, and we want to find the proportion of the 130 adults that had a temperature below that. So it's just a count, right? 2 and 3 is 5, and 5 is 10, and 9 is 19. So 19 out of the 130 adults had a temperature below 97.5 degrees. And there's some notation that we'll be using here for the rest of the semester, so it's good to see it right away. So I would say, the way I write this, I would write the proportion, PR, or we can even say probability if we grabbed a random adult, but I'm thinking proportion here. So the proportion of adults that had a temperature below 97.5 degrees is 19 out of 130. Or if you write that as a decimal, punch it into your calculator, it comes out to be about 0.1462. So about 14.6% of the people in the sample had a body temperature below 97.5 degrees, right? Okay, not too hard. Question 3 is similar. It says, find the proportion of adults that had a temperature below 100.5. So PR, the probability or the proportion who had a temperature below 100.5 degrees. Okay. All right, and let me find 100.5 degrees. So we're looking for everybody who has a body temperature below 100.5 degrees. Okay, that's a lot, right? So I could add these numbers up. 2 and 3 is 5, and 5 is 10, and 9 is 19, and 9 is 28, da, 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 da. I could add them up, or I just know that there's 130 total healthy adults, right? And I'm only leaving off one, so it's going to be 129 out of 130, or about 0.9923 if you punch that in your calculator. Okay? All right. One more warm-up question. It says determine the proportion of adults that had a temperature between 97.5 and 100.5. Okay. So a couple ways to think about this, right? So we're trying to find the proportion of the adults that had a temperature between 97.5 and 100.5. So I'm going to write this as the proportion that had a body temperature between these. So the temperature is greater than 97.5 and also less than 100.5. Okay? So again, the notation might look a little confusing, but it is really helpful for us. So my temperature is greater than 97.5 and less than 100.5. All right, so I want to find that proportion, and as I said, there's at least a couple ways you can think about it. First of all, I'm looking between these two values, 97.5 and 100.5, so I can add up the frequencies. 9 and 23 is 32, 32 and 18 is 50, plus 22 is 72, plus 20 is 92, plus 11 is 103, plus 5 is 108, plus 2 is 110. So I get 110 over 130, or about 0.8462. Okay? All right. The other way I can think about it, well, there's at least a couple other ways I can think about it, but one way that I like to think about it is, okay, I just found the proportion that was less than 97.5, okay, and there were 19 people who had a body temperature less than 97.5. And I also found there were 129 total that had a temperature below 100.5. And so think about that. I want to find the number in between. I want to find the proportion in between, but to do that I have to find the number in between, the number of people in between these two values, right? There's 19 below 97.5 and 129 below 100.5. So the difference between those two is how many are between 97.5 and 100.5. Okay, so I could do 129 minus 19 to get the 110 as well. Okay, that's a really useful way of thinking about it. Okay, all right, so there's our warm-up. So now I want to think about the problem in a different way. Okay, so going back to the picture of our histogram, I asked you at the beginning about the shape of it, and if it's not clear, it should be that the shape of this distribution, right? It's a normal distribution, right? It definitely has that that beautiful symmetric mound shape to it. It's not perfect, not by any means, but we can see that mound shape, right? You know, I can, for example, fit, at least roughly, I can fit a normal curve to that distribution, right? Okay, so I want to talk about the normal distribution just a little bit in general, and then we'll get back into the problem. Okay, so first of all, when I draw that smooth curve, okay, it's what we call a model. It follows the approximate shape of the distribution, but it's not perfect. Okay, we never have that perfect shape. But what we do is we use the normal distribution as an approximation to model the distribution, okay? Now, all normal distributions have that symmetric mound shape, okay? So if you have a true normal distribution, then it will have that shape. Not all of them are exactly alike, and there are two things that distinguish one normal distribution from the other. Okay, so think for a minute about what those two things are. Okay, when you move from one normal distribution to the other, the two things that distinguish them from one another are their mean and their standard deviation. Okay, so the mean, right, is the center of your normal distribution, right there. And then your standard deviation is telling you how spread out your data set is, right? So a small standard deviation will give you a skinny and tall normal distribution, normal curve, and a large standard deviation will give you a short and fat one, okay? And if it's fat and short or tall and skinny, the big point is you still think of these as being bar graphs, right? Frequency histograms, right? And the total area under every curve is 100% of the observations, right? So that's why if it's skinny, it's got to be tall, and if it's short, it's going to be fat. Okay. All right. One other important property is that the distance from the mean to the point at which the curvature changes is one standard deviation. Okay. And what I mean by that is, if you're around the mean, the normal curve, the shape of the curve is concave down, right? So it's curved downward. And then when you're out on the tails, it's curved upward. Okay? And so somewhere in between, it goes from being curved downward to being curved upward. And right at that point is what they call, is one standard deviation out. Okay? So if you go one standard deviation above the mean, you'll be at that inflection point, that point where the curvature changes. And if you go one standard deviation down, you're at that same point. Okay? Okay. One quick example. You can look at problem 12-1, part J. Again, just a little bit of a tangent here. Here's a situation. It says the normal curves in the figure below give the distribution of exam scores for 3 different classes. Okay, one class has a mean of 70 with a standard deviation of 5. One has a mean of 70 with a standard deviation of 10. One has a mean of 50 with a standard deviation of 10. Okay, so these are our 3 curves, and your job is just to do the matching. Okay, so take a minute, pause the video, and do that if you haven't already. Okay, and then the thing to note, right, is standard deviation of 5 is going to be a more condensed or a more consistent data set, right? A smaller spread. So you're going to get a skinny and tall distribution, and 100% of the observations lie under that curve. Right? Our other 2 curves, our other 2 normal distributions, are shorter and fatter because their standard deviation is larger. Okay, one has a mean of 70, right at the center, so that's this guy. And one of them has a mean of 50. And so that's the center of the line of symmetry for that shorter and fatter curve. Okay? So there's our distribution. So here's the amazing thing about the normal distribution. Not all normal distributions have the same shape, right? The thing that distinguishes them is their means and their standard deviations, right? But all of them contain all the observations below them, right? And so we have this thing like the empirical rule, 68, 95, 99.7 empirical rule. Now we can use that idea, that same idea, and extend it. Okay, so if you haven't done it already, please make sure to read pages 250 through 252 of the text. Okay, I'm going to talk through that briefly here as a demonstration, but you really sort of need to read it to make sure that stuff gets into your head, especially about this use of our table. Okay, and then on our worksheet, there's just a couple of observations about the normal distribution, right? So what we can do is we can use our empirical rule. And then even more, if we have any z-score for an observation, we can approximate the proportion of scores falling below that value of z. Okay, and then table 2 in the back of our book will tell us how to do this. Okay, and then using that and some geometry, we can always find the proportion of values above or below any z-score, and even the proportion of scores between any two z-scores. Right. Okay, so let's see how that works. All right, so we're back at our problem. Okay, and what we're going to do is we're going to find these same three proportions, okay, that we found by hand, right? By counting and calculating proportions directly, we're going to approximate those values using the fact that this is roughly a normal distribution. Okay, so first thing I'm going to do is I'm going to calculate the z-score for the value 97.5. Okay, so I want to answer this first question. I want to determine the proportion of the adults that had a temperature below 97.5. I'm going to find the z-score for 97.5. Right, so remember how we find a z-score? We do the observation minus the mean over the standard deviation. So my observation is 97.5. My mean is 98.249. And my standard deviation is 0.733. My z-score ends up being about, because I'm rounding, negative 1.02183. Okay, now remember what that means, right? That means it's negative, it's got a sign, right? And the sign being negative means it's below the mean, right? 97.5 is below the mean, okay, not surprising. And the 1.02 is the number of standard deviations were below the mean. Okay, so our z-score is negative 1.02. That says we're 1.02 standard deviations below the mean without observation. Okay. Okay. All right, so I want a bigger picture here. All right, let me zoom out a tiny bit. All right, good. All right, so we got our z-score is negative 1.02183. All right. Okay, so the problem on our worksheet asks us to shade the region corresponding to body temperatures below 97.5. Okay, so we already did this when we were thinking about this as a bar graph, but now I'm just going to shade those observations. Okay, and then I know there's 100% of the observations below the whole curve. Okay, I want to know what that area is. Okay, and that's what table 2 is going to do for us. Okay, so table 2 is at the back of your book. All right, and it's called Standard Normal Probabilities. And what it does is it gives you the area under the curve, the proportion of observations under the curve to the left of the given z-score. Okay, so let me see if I can get a slightly bigger, better picture of this. Okay, on my other feed here. Okay, and so if you notice the z-score, it's a little tricky to read, but the first column here gives us the z-scores with the units and the tenths digit, and then these other columns give us are for the hundredths digits. So, and then the values in the table are the proportions corresponding to the area to the left of the given z-score. Okay, so for example, we are looking for negative 1.02183. Now we can't go any farther than the hundredths digit. That's as far as good as the table does for us. But I'm going to scroll my way down until I get to negative 1, okay, negative 1.0, and then I want negative 1.02. That's as good as we can do. So there's negative 1.00, negative 1.01, negative 1.02. So that is the proportion of observations to the left of a z-score of negative 1.02, right? So then, got to remember that, 0.1539, Okay, so then if I want to know the proportion of observations of temperatures less than 97.5 degrees, that's what I'm looking for, right? Okay, that's going to be approximately the same as the proportion of z-scores that we get that are less than 1.02. Okay, and I only said approximately there because I've rounded to 1.02. Okay, and we got about 0.1539. Okay, that's not bad, right? Because that compares to what we got when we found this, using the histogram. We got the proportion of observations less than 97.5 degrees to be about 0.1462. Okay, it's not perfect, but again, remember the normal distribution is a model, right? It's not a perfect match. Okay. All right. Good, and that's how we use table 2. All right, let's do the other 2 problems. All right. Again, you should try them if you haven't tried them on your own yet, as practice. Okay. So second part, right? We want to use table 2 to approximate the proportion of adults that had a temperature below 100.5 degrees, and we found using the histogram. We found the proportion was the proportion of body temperatures less than 100.5 degrees was approximately, what did I get? 0.9923, 99%. Okay, so now let's use table 2 and the fact that it's a normal distribution. Okay, so we're talking about 100.5, and I want the proportion of adults that had a temperature below 100.5, so I'm looking at that whole area, right? It's a huge proportion, right? Right? Only a few observations would be above 100.5. Most of them would be below. Okay? So what we'll do is we'll find the z-score for 100.5. So my z-score is my observation minus the mean divided by the standard deviation. Okay, so it's going to be 100.5 minus 98.249 divided by 0.733, and we get about 3.0709. Okay, and so the proportion of observations where the body temperature is less than 100.5 is going to be approximately the proportion of z-scores less than 3.07. I can only go as far as the hundreds digit, so I rounded. Okay, and that's going to come out to be approximately, well, let's have a look. Okay, so I want to go find negative, or I have to find positive 3.07, so it's going to be on the second page of my table 2. There's 3.0, 3.00, 1, 2, 3, 4, 5, 6, 7. So I get 0.9989. Okay. Again, not a perfect match, but pretty close, right? Okay. All right. Okay, one more. So it asks us to approximate the proportion of the adults that had body temperatures between 97.5 and 100.5 degrees. Okay, so let's see. So I'm going to shade that region. Okay, so we want to find the proportion of observations that are between 97.5 and 100.5 degrees. Okay, and we did that using our histogram if you remember at the beginning, we got that this proportion was approximately 0.8462, right? Okay. So we can do this one as well using our normal distribution. It seems kind of scary because the table 2 only gives us areas to the left, right? So how do you do an area between? Okay, so here's a way we can think about it, right? We're trying to find the area between, or the proportion of observations between 97.5 and 100.5. Now look at what I have, okay? I've already found the proportion of observations to the left of 97.5. And I've also found the proportion of observations to the left of 100.5. So how are those related? Right? We know the area to the left of 97.5. I know the area all the way to the left of 100.5. So if I want to find the area in between, I can just subtract. Right? So this is equal to, at least approximately equal to, what do we get for our previous answers? We got the area to the left of 97.5, or sorry, to the left of 100.5 is 0.9989. Okay. We found the area to the left of 97.5 is 0.1539. Okay. I subtract those two values and I get 0.8450. Not perfect, but actually darn close. Okay? So that's how we use Table 2. We'll get lots more practice on using Table 2 in the next activity, and we'll also talk about using an online applet that will help us with it as well.